Hi guys, BuildZoid here, and today we're finally going to be taking a look at the Z490 voltage regulation spreadsheet. Basically, I've measured most of the motherboard. Well, the only motherboard that's missing from this list that I have is the Z490 Master, and the reason why the Z490 Master is missing is because it's basically the same VRM as the Z490 Aorus Extreme, and I see no good reason to test two of the same motherboard. So yeah. That's why that's not that's why that's not in the spreadsheet. So, with that out of the way, I guess I need to explain how this works. Oh man. So, basically we have a bunch of measurements here. So the only measurement that actually matters, which is why it's highlighted, is the average to minimum voltage measurement right here. Well, that's not a measurement, that's actual like data processing. These are measurements from the oscilloscope. The oscilloscope that I used is a Rigol DS1054Z. It was set to 100 megahertz bandwidth because I have it unlocked, and then 10 milliseconds per division and 50 millivolts per division. So yeah, the biggest problem with the oscilloscope is that it only measures down to 10 millivolts, or the measurement function only goes down to 10 millivolts on voltages over 1 volt. So the problem with that, of course, is if you have something like 1.27 volts versus 1.28 volts and you're trying to make a comparison between the two, 1.27 can be 1.265 or it can be 1.274, 1.28 can be 1.275 or it can be 1.284. So basically, this looks like a 10 millivolt difference, but it could be as small as a 1 millivolt difference, and it could be as big as a 19 millivolt difference. So that's one of the major issues with the oscilloscope I have. Technically, there's a bit of a workaround that I could have done for that, which is to run the same tests with slightly different voltages multiple times. So instead of just, doing everything with the goal of hitting 1.32 volts on the average oscilloscope measured voltage, I could have done like a test at 1.32, 1.34, 1.36, and then that would give us more data, which means the sort of inaccuracy wouldn't go away, but it would get smoothed over a bit, because if you well, for comparison purposes, it would be better. Like, it still wouldn't change the fact that the measurements are to 10 millivolts, but if there's like one measurement that's kind of like looking a bit weird, then having multiple reruns of that same measurement but at different voltage levels would sort of, smooth over that irregularity in the data. So speaking of data irregularities, this row right here isn't using exactly the same test methodology as any of the other rows on this chart, which is why we have this note over here. And that row is not using the same methodology because I'm lazy, and that's also the same reason why I did everything with one average voltage instead of multiple different average voltages. So yeah, that's a bit of an issue. Also, if I had a better oscilloscope, then actually the 10 millivolt, like this wouldn't be a problem if my oscilloscope just went down to 3 decimals, but it doesn't, so yeah. Because the Rigol DS1054Z is a sort of very cost-effective scope, but that doesn't mean it's very good. Yeah, so I really kind of need a like, if I want to do this testing better and spend less time on it than in the future, I basically just need an oscilloscope with more resolution. That's it. I don't even need more bandwidth. Like, if you read the Intel documentation, they recommend testing at well, actually, depending on which Intel documentation, like some of the older platforms, they tell you to test at 20 megahertz bandwidth. Some of the newer platforms, they recommend testing at 100 megahertz bandwidth, so that's no problem. And in terms of the probe that I'm using, I actually just had a bit of coax going all the way to the CPU. So we don't have to worry about like having a 10x probe that doesn't I'm not using a 10x probe. This is all 1x with coax, and it's 50 ohm termination at the oscilloscope. Right before the oscilloscope, I have a 50 ohm termination because the Rigol doesn't have internal 50 ohm termination. Which also would be something that I'm kind of thinking, like, yeah, if I got another new scope, I'd like one with internal 50 ohm termination. Not that I'm not sure that would make a massive difference, but it could be better. So anyway, That's kind of the limitation of the test equipment and the measuring methods I've used. The CPU I was using for all of the testing was a 10700K at 4.9 gigahertz core, 4.4 cache. The reason it's not running higher frequencies is because the chip kind of sucks, and I am 99% certain that it would have crashed on this test. Maybe on this one too, but definitely on this test. This is really low. This might have also been a problem. That could have also been a problem. So because I'm running up to LLC levels that are just completely useless, yeah, I didn't want to test with super like high frequencies because, well, the thing is going from 4.9 gigahertz to 5 gigahertz or even 5.1 gigahertz, which the chip doesn't do 5.1 for LinPack, so that's not an option, but 5 gigahertz wouldn't really change the power draw behavior of the CPU at all. So yeah, it's important, like running the chip at 4 gigahertz, that would actually significantly reduce the power draw, but 4.9 versus 5 gigahertz is basically the same thing. So that's not super concerning. In terms of how you're supposed to read this chart, well, the simple way is we're just going to hide this column because that column is mostly for me to do the measurements. Actually, you know what? No, let's not get to that. So the first thing we'll address is maximum voltage measurements because those are nice and simple, especially with this data set because none of these motherboards have a overshoot problem whatsoever. The max voltage never goes anywhere near like concerning levels. So we can basically look at all the maximum measurements and go like, okay, this is just irrelevant. We can ignore it. So the maximum voltage while running any of these workloads, like, well, worst case scenario is LinPack. As you can see, it consistently gets the highest maximum voltage measurements. And the thing is, none of these are high enough to be concerning. Like, this is all in the slightly above 1.4 volts range, which, like maximum voltage is concerning for potentially the longevity of the CPU, but it would have to get really, really high because this is load release overshoot that we're looking at here. So this is caused by the CPU pulling very little current. So the only real concern with having a lot of overshoot is like, if it gets high enough, it can start damaging the gate oxide and the insulation inside the CPU. 1.4 volts is nowhere near high enough, so that's not a concerning. Now you might point out, but BuildZoid, you're running a relatively low dye sense voltage during all of this testing. With a higher dye sense voltage, wouldn't you get more overshoot? Yes, you would, but even if I was running a dye sense voltage of, say, 1.4 volts, our maximum overshoot would still be under 1.6. And as long as we're below 1.6, I just straight up don't care. Also, 1.4 volts dye sense is ridiculously hard to cool and not safe for long-term use. So that's not really something I would be worried about anyway. So that's like an unrealistic workload. Well, okay, no, if you had enough cooling, you could get away with 1.4 volt dye sense, but you don't have enough cooling. So yeah, and in that scenario, yeah, we might start approaching the 1.6 volts level on the LinPack runs, but even then, that's not super concerning because, yeah, that's what, 150 millivolts more. So that would be like, this would be like 1.66. There would also be slightly more current going into the CPU, so it might end up being more like 1.68. Wait, no, 1.58, right? So as long as it's somewhere around 1.6, I'm not concerned with the maximum voltage level. This isn't concerning. I had Z370 motherboards that were hitting like 1.7 overshoot. I think it even hit 1.8 at one point. That motherboard was really bad. That's the kind of thing that I watch out for with the maximum measurement is like if the motherboard is, you know, hitting well in excess of 1.6 volts, it's like, yes, now we have a problem. This is concerning. This might be bad for the health of the CPU. But this is 1.4. It's just like it doesn't matter. So yeah, with that out of the way, we can hide it because like every single one of these boards is doing something in the 1.4 range. I guess you could say that the Aorus Extreme is kind of doing the best job, along with like the Apex. Those are the boards doing the best job. The Unify is kind of doing the worst, along with sort of the ITX Ultra and the Vision G, right? Well, that's an override mode, and override mode is a bit special, but yeah, like it's like none of these values is high enough to be concern worthy, so we're just gonna hide all of the maximum columns because they don't matter. Bam. So yeah. Well, the funny thing is, if your VRM also has a ridiculous amount of overshoot, then the controller is gonna struggle to like regulate the voltage going to the chip. But that doesn't, like, the reason why that would be concerning is not because of the actual overshoot level. That's concerning because of what happened, like, on the, like, what it can lead to excessive undershoot if you have excessive overshoot, because the controller is going to like, the controller is going to see the excessive overshoot and it's going to start trying to compensate for that. And if the CPU suddenly goes right back into pulling a ton of current out of nowhere, then the VRM might still be trying to compensate for a bunch of overshoot while the CPU is ramping up to full current draw, and so you get excessive undershoot after that, and then that causes, like, further instability on the CPU. So we don't have to worry about overshoot. Like, overshoot is just kind of like, and the thing is, like, we have undershoot measurements, so I don't care about the overshoot measurement, right? From a regulation perspective, it's just kind of like a health perspective for the CPU, and it's fine. None of these boards was anywhere near concerning levels of overshoot. Or, like, even if we scaled up the voltage, it still wouldn't be concerning. So, that's kind of that. Now let's talk about how to read the important part of this. So you can ignore the DyeSense column, basically. And the reason why you can ignore the DyeSense column was the DyeSense column was for me to make sure that all of the motherboards are running almost the same settings. And I say almost the same because, well, yeah, you can see they're kind of slipping all over the place. Like, the Apex, the thing is, the Apex uses a completely different DyeSense measurement system from any of the other boards. All of the other boards, I'm getting a voltage measurement directly from the voltage controller. With the Apex, there's an op-amp that replicates the voltage measurement to the Super I/O, and the Super I/O has 9 millivolts of resolution, which is not enough resolution. The controller has 2 millivolts. So, yeah, the Apex is probably pretty close to the 1.26 that, like, the Xtreme and everything was getting, but because it uses a Super I/O measurement, it reads low. Or it might be reading, I don't know if it's reading low or high, because, again, it's just like, well, this doesn't have an equally accurate measurement to anything else. And again, this is something that would have been possible to compensate for with more test data. And now that I think about it, you know what? In the future, I should just ditch the super high voltage test and focus more on LLC levels that actually, or super high, like, super aggressive LLCs. Like, I just shouldn't test them in the future, and I should focus more on getting better data for the LLC levels that actually matter, because you shouldn't use Ultra Extreme. You shouldn't use level 7 or level 8. You shouldn't use, what is it, mode 3 to, well, with the Unify is so annoying. So if you have a Unify, if you don't have a Unify, you can just basically, like ignore all, like, you can just ignore all this stuff, because the Unify has, like, MSI apparently tried to kind of copy the DyeSense thing that Asus does, but they did it really weird. So instead of having DyeSense, they have, like, VCC sense, and it's still, like, the measurement is still inaccurate. Okay, like, it's still nowhere near DyeSense. And then they have also socket sense, and the problem with it is, for some reason, it affects the load line settings, which is, like, it shouldn't do that as far as I'm concerned. But it does, because I have no idea what they did. But anyway, if you have a Unify in the BIOS, you have the option to have the board running in DyeSense or socket sense or VCC sense. And yeah, it changes how the LLC slopes work. So with VCC sense, like mode 2 or 3, you shouldn't be using them. And with, or even mode 4, like, you shouldn't even be using mode 4 now that I look at the numbers. Yeah, like, even mode 4 is not, like, these three, there's no point using them. And then if you're on socket sense, well, I didn't test mode 2 and 1 because the Unify has too many settings to test, and I'm lazy again, so I just kind of did, like, I saw mode 3 was already, like, mode 3 was already matching, like, mode 5. So I was like, yeah, if we raise this to mode 2, this isn't gonna, like, mode 2 probably won't make any sense, and mode 1 definitely won't make any sense. So anyway, yeah, and then the ITX board only goes up to turbo, so that's, oh no, and with the Gigabyte boards, I just kind of decided, like, the thing is, these perform so similar to the Xtreme on the reasonable LLC levels, and turbo is debatable as to whether it's a reasonable LLC level. So I didn't see a point in testing Xtreme and Ultra Extreme, because we already know from the Xtreme that Ultra Extreme and Xtreme suck, and it's not like these boards are going to do a better job. Or even if they did do a better job, it's not going to be better by a large enough amount to justify using Xtreme or Ultra Extreme LLC. So there. So yeah, DyeSense voltages were mostly for me tracking that the motherboards were running roughly the same settings, so we can hide all of that. Bye-bye. Actually, we can hide the idle as well. Or, yeah, we can hide the idle. I don't really see the reason to look at the idle values. So we're just going to hide both of those. And we could arguably, the thing is, this is actually against minimum, but yeah, so I think at this point it's pretty self-explanatory, right? These are different workloads. The plus mouse just means I was moving the mouse while the workload was running, because if you just run Prime 95 16K FFTs on its own, it's relatively quiet in terms of, it's relatively consistent in terms of its power draw, and so there's not many large transients for the VRM to have to deal with. But if you start moving the mouse, then Windows handling user input stalls out Prime 95's worker threads every so often. And when it does that, it causes voltage regulation issues that bottom out at like 1.19 volts on level 8 LLC. So yeah, same thing for LinPack and 112K FFT size. Though LinPack is naturally noisier than Prime 95. So like moving the mouse in LinPack makes less of a difference, but it still makes a difference. So yeah, that's why it has plus mouse there. Anyway, so these are just the workloads I was running. And basically the goal here is for the average voltage and the minimum voltage. So this is minimum on average because these are multiple samples. Like this is multiple samples. Basically each test would be run for at least 30 seconds while I was moving the mouse. And I would track the average voltage during the 30 seconds. So the scope would average the voltage over the course of those 30 seconds. It would average the minimums that it would see. So, the way the scope works, it takes a minimum measurement every time it updates the waveform. And so we'd get, so sometimes we'd have minimums that bottom out at like 1.3. Sometimes they bottom out at 1.29. And that's why like the average minimum is always higher than the minimum, except when I didn't remember to move the mouse, because yeah, if you don't move the mouse, Prime 95 is actually really consistent, and so the average and the minimum end up being the same thing. If you start moving the mouse, then the worst case scenario starts, getting lower. And you can actually sort of see that in LinPack as well, where it's like, yeah, moving the mouse made it a little bit worse. Interestingly, yeah, so yeah, this is another thing where it's like, oh yeah, imagine if I had done measurements around a larger voltage range, that would have helped. But anyway, like the thing is, a lot of these results are so close together that like, yeah, there's a few numbers that you look at and it's like, oh, this doesn't make a ton of sense, and it's like, yeah, it doesn't make a ton of sense. But honestly, even if I reran that to get more data into it, if it spreads apart by 10 millivolts, it's like, who cares? It's 10 millivolts. It's not a big deal. What would be a big deal is if there was like a 50 millivolt advantage in favor of some motherboard compared to another motherboard. That's a big deal because that's now you're talking about a significant amount of power consumption, significant amount of voltage, so yeah, but 10 millivolts is basically irrelevant. So as much as I am still annoyed that, there is a bunch of error on my measurements because my oscilloscope isn't expensive enough or good enough. Just because something is expensive doesn't mean it's good, okay? But unfortunately with oscilloscopes, there's a very tight correlation between the price and the capabilities. So, yeah, anyway, where was I going with this? Right, so like, yeah, so some numbers like this don't make a ton of sense, but it also doesn't make it doesn't matter too much. So I'm not too annoyed about that. But anyway, so yeah, basically we want the average and the minimum voltage to be closest together. The minimum average is, I'm actually not sure why I was tracking it. I could have just, well, no, I'm still happy that I have that measurement, but it's like, I don't know why I'm showing it to you, because quite frankly, it's pretty much irrelevant. Well, okay, it's not completely irrelevant, because there's, like, this will happen. Like, you'll get the average minimum basically without moving the mouse at all, right? Like, you'll still get this right here without having to do the plus mouse part. Now, if you start moving the mouse, that's when you get the really, really bad worst case scenario minimums. And so it's kind of like, yeah, so if you don't move the mouse during Prime 95, then it's like you're going to be limited, your stability is going to be limited by this column, whereas if you start actually moving the mouse, then it's going to be limited by this column, because that's where you start seeing the mouse really make a difference. Um, but yeah, so that's kind of that. And now you might be wondering, okay, wait, why do we want these two voltages to be closest together? Well, because your CPU crashes when the voltage is too low relative to the frequency that your chip is running at. And well, if you know, so like here, right, we're running we're running 1.32 volts average. So our chip, you know, like this is the, like if you looked into, well, actually, if you looked at your voltage reading on the apex, you'd be looking at like 1.25 volts, but that's still the same voltage, right? So you'd be like, okay, we're running 1.25 volts, we're running 1.25 volts, except in this case, you have, what is it, 70 millivolts of undershoot. Right, so the absolute minimum like on average, your minimum voltage would be like 1.18 or something. Potentially even worse, because the reason why this measurement, this voltage level is higher than the dye-sense voltage is because the coax goes to the CPU substrate. It doesn't go directly behind the CPU die. So the measurement is a little bit high because there's still resistance in the substrate of the CPU itself. So that's kind of like, you know, further just limitations of the test equipment. Well, actually, I don't really think there's a like reasonable way to work around this limitation right here. There's just not really much I can do about that. Because trying to, well, you could potentially take measurements off of the dye-sense circuitry of the motherboard, but that's incredibly annoying to do, and I'm not doing that. Like, I tried to do that on X570. I'm not trying to do that again. It's an absolute nightmare to take measurements that way. So we're not doing that. But anyway, so the point is, now this is 1.25 volts on average. This is also 1.25 volts on average. So the CPU is pulling the same amount of power in both scenarios, except here, you know, your CPU on load transients is going to be hitting 1.18. Whereas here it's going to be hitting like, or even potentially even like 1.27 or lower. Because the thing is, there's a bit of attenuation that goes on the further you, like the further away from the CPU die you take your measurement, the more it attenuates the voltage spikes. So it attenuates the downward spike, it attenuates the upward spike. And so if we were measuring all the way at the actual die itself, we would maybe see more undershoot rather than, you know, like here I'm seeing like this is a 70 millivolt gap. If we were measuring at the die sense, it might be like 80 or 90 millivolts. It's not really a huge difference on like from some motherboards where I have actually done die sense versus, you know, relatively close to CPU measurement testing. The difference isn't massive, but it is there, and it's kind of like, yeah, so it would potentially be like the voltage would be undershooting down to say 1.2, like to simplify it, let's just say 1.27. Whereas here, this would be bottoming out at 1.23, right? Like because this is a 20 millivolt gap. There's only 20 millivolts of undershoot. There's basically no undershoot, right? Like there's almost no undershoot on this. So here you'd be getting a minimum voltage of 1.23, and here you'd be getting a minimum voltage of 1.18, right? And so if you wanted, and if your CPU actually required exactly 1.25 volt, or, well, let's say your CPU required 1.23 volts minimum in order to run whatever frequency you're trying to run, well, here you would have to run, like, because this is going to be hitting 1.18. Right? It's not going to be hitting 1.23. It's going to be hitting 1.18. This is going to be hitting 1.23. So in order to get it stable at level 8 LLC, you'd have to crank up the voltage. So we want the average voltage and the minimum voltage and the minimum average voltage to be as close together as possible. Like ideally, there wouldn't be any difference at all, but because of how CPUs work and how physics works, there's always going to be a bit of a voltage difference because, yeah, CPUs are not like CPU. You can mostly model the power consumption like over long periods of time. The power consumption of a CPU behaves a lot like a resistor at a very, very, you know, very low time scale or very small time scale. The power consumption of a CPU is Still kind of like a resistor, except if the resistor was changing its resistance very, very quickly and at random and in very large, like by very large amounts. And that causes the massive voltage regulation issues because of just how VRMs work. So, yeah, and even if you had like, well, like just anyway, we're not going to get into that. So, let's hide that column because it's not relevant. And quite frankly, we're just going to hide the minimum. Well, actually, we could hide everything that isn't the A2M value at this point, because this is really the only value that you know is super super important. So anyway, let's say you have an Apex. What kind of LLC levels should you run? Well, you can run up to level 6 because, yeah, as far as my oscilloscope is concerned, level 5 has the issue of like it was technically not running the same difficulty of test. So level 6 is fine as far as I'm concerned. It seems to be maybe 20 millivolts worse on 16K FFT size with the mouse movement. But then there's also like this is slightly higher like average voltage, and it's like you know, maybe this was really borderline. So maybe this would have been 1.28 to 1.32, and then it would have been 0.04, which would have been closer. Anyway, but yeah, so so in 16K FFT size, it looks like there might actually be a somewhat significant difference between level 4 and level 6. When you get to LinPack, though, they're the same. Like they're just straight up the same. And when you get to 112K FFT size, they're almost the same. So I'd say level 6 and level 4 are still very comparable, and level 5 should be about the same as level 4, or like should be somewhere in between the two if I had actually done and retested it. Because right now it looks like level 5 is better than both of them. But that's kind of like, well, I was also not doing the test properly for that level at the time. So the order that the tests were run in was like I ran level 4, level 5, level 6, level 7. Then I remembered, wait a minute, we need to move the mouse if we want to get the really, really nasty transients. So I reran level 6 and level 4, and then I was like, yeah, level 5 is going to be somewhere in between. And that's why level 5 never got rerun. So level 6, so on the Apex, level 4 to 6, perfectly acceptable. Level 7, 40 millivolts worse regulation than level 6. That's like a significant amount of voltage. Basically, in order to get the same minimum, like worst case scenario minimum, you'd have to be running 1.36 on average to get the same voltage regulation as like, you'd have to run, 40 millivolts more. So instead of 1.32, you would have to run 1.36. And you might be like, but that's 1.33 builds. Like, yes, I know. I'm aware, but we're doing the comparison based on this, right? So because if I actually wanted to match that 1.28 over there, then it would be plus 50 millivolts, and this would be 1.37 in order to get these two values to align. This is all testing I've done in the past. So if you're like, where are you pulling all of this extra data from? I've been doing these kinds of measurements for a while now. So yeah, like unfortunately, this is very much off the deep end. Anyway, yeah. So level 7, 40 millivolts worse, which isn't a complete catastrophe yet. Like 40 millivolts, that's a noticeable amount of power consumption increase, okay? And the reason why I say that's a noticeable amount of power consumption increase, I don't know why the calculator opened that big, but basically if you went from, say, you went to, 1.36 versus 1.32, right? So that's a 3% increase in power draw. You square that. So that's a 3% increase in voltage, which translates to about a 6% increase in power consumption. That's relatively significant. That's not something you can just it's not a huge deal, but that's starting to get into the range of like, okay, this is actually gonna noticeably start driving operating temperatures up and that kind of thing. So yeah, level 7, definitely not ideal, but by the time you get to level 8, like 0.13, 0.1, and 0.14. So compared to level 6, which level 6 is, not doing, like level 6 is already not doing as good, like not always as good as level 4. Admittedly, in the sort of hardest test, it's doing okay. It's kind of funny how some boards do better on 16K. Like you'll notice it as we go through that some boards do better on 16K than they do on LinPack, and sometimes it switches around. Anyway, So yeah, like if you were on level 8 though, right? So that's 0.13 versus 0.5. What is that? That's 80 millivolts. So you'd be running 1.4 volts instead of 1.32 volts. And at that point, we like it's not even that's 12% more power consumption. That's a hell of a lot of more power consumption. So yeah, at that point, it's definitely a big deal. So level 8, awful. Don't use it. There's never a reason to use it. Like, I don't know why you'd ever want to use level 8. Level 8 is horrible. Level 7 is also pretty horrible. Level 6 is fine. Level 5 is fine. Level 4 is fine. If you're not running out of voltage range, I would probably just stick to level 4, right? Like, depending on where you're, like, how your cooling is working out. Like, I would basically, if I was overclocking a 10700K or 10900K on the Apex, what I would do is I'd punch in 1.45 volts, and then I'd set it to level 4. And if it's, not stable at whatever frequency, like if I have cooling headroom and it's not stable, then I'd go up to level 5. And I wouldn't even change the voltage, right? Because I'm assuming I have cooling headroom. And if that fixes the stability, great. Maybe we can raise the frequency some more. And by level 6, if you're at 1.45 volts, you're probably going to have cooling issues. Because how much V droop is that? That's 90 millivolts. Now, that's 110 millivolts of droop. So 1.45 minus 0.1. The thing is, the droop increases as the current draw increases, so I'm going to assume it's going to be like more like 1. It's not going to be 0.11 anymore. It's going to be like 0.12 or 0.13 maybe. If you're on a 10900K, so that'll give you like 1.33 volts die sense, which is a pretty high voltage to run on a 10900K, depending on what kind of cooling system you have. So yeah, I wouldn't like. You might be like, but that's a lot of E droop. It's fine. Like you're still getting plenty of voltage under worst case scenario. Like you're not really like for day-to-day usage, I consider that a perfectly acceptable amount of full load voltage. So yeah. Anyway, where was I going with that? Yeah, so like level 7 and 8 are just unusable. I'm kind of annoyed that the Apex doesn't have a good like there's no level 6.5. Right? Like there's a really big gap between 1.36 volts and 1.28. That's 80 millivolts. And on level 6, like the board is still doing so well that I think maybe a level 6.5 would have made a lot of sense. Maybe they should have just moved level 7 up closer to the level 6 because level 7 and level 8 are really close together, right? This is 1.28 versus 1.25. I think this would have made more, like level 7 could have been like 1.3 or 1.32 volts, in my opinion. That would have made it, like that would probably get it pretty close to level 6. You wouldn't get this massive 40 millivolt voltage regulation penalty. Right? Admittedly, in Linpack it's only 20, but then in 112K it's again 40 millivolts. So yeah, it's not great. Level 7's really not great. I think they should have probably made it like level 7. I think should have been droopier. Because also like the LLC steps, and what I really don't get is like why do we have level 1, 2, 3, and 4? Like level 4 already needs 1.44 volts to get 1.25 volts die sense. That's what is that? That's like 190 millivolts of voltage droop. Like if we were on level 3 or 2, like I level 1 or something, I'd be punching in 1.6 volts to get 1.25. Like this is a yeah, so the Asus LLC range is kind of whack. Is one way I'd put it. Is like they have a lot of levels that I wouldn't use because they're too low, and then they have level 7 and 8 where it's like, could we have something between 6 and 7? Thank you very much. Anyway, but it's not a huge deal. Like level 6, I think is fine. So yeah, so that's cool. Moving on to the Aorus Extreme. So compared to the Apex, the Aorus Extreme seems to be a little bit worse, right? At least in 16K FFT size, it seems to be a little bit worse, like 10 to 20 millivolts, depending on which exact. Well, these two are the same. This is 10 millivolts, and this one doesn't count because that was on a different test methodology. So they're like the Apex might be slightly ahead by like 10 millivolts, maybe. Again, I wish my oscilloscope was more sensitive or I was less lazy. Either of those two would be great. Anyway, Linpack, they're the same, so that's kind of fun. Like, they're literally the same, so that's cool. And then 112K, the Extreme wins the first test. Like the first, yeah, the Extreme does better, then it does kind of worse, and then it does then it does better again. So I would consider them tied. The Extreme really seems to do much better in very noisy workloads. Like 112K and Linpack are both extremely noisy compared to 16K FFT size. Um, and yeah, the Extreme seems to just be handling that really, really well. Um, whereas the Apex just kind of doesn't, I guess. So that's really interesting to me, especially because like the Apex actually has uh, the Apex uses way more multilayer ceramic capacitors in its CPU socket cavity. And it's like, so you'd think that would actually do better in the really noisy tests, but apparently no. If you just whack a couple pause caps in your socket and then slightly up the power plane, you just kind of do great in Linpack and 112K FFT size, and then for some reason you don't do so great in 16K FFT size. Anyway, so with the Extreme, you should probably stick to low, medium, or high in terms of LLC levels. Right? High is not quite the same as level 6 on Asus. Actually, even medium is slightly droopier than level 5. Turbo LLC, again, like I really wish this was like 1.34 instead of 1.32, but yeah, it's 1.32. Turbo LLC, you get a 30 millivolt penalty for Prime 95, you get a 20 millivolt penalty for Linpack, and you get a 30 millivolt penalty for 112K Prime 95. So Turbo is not as bad as this jump from level 6 to 7 on the Asus board, right? Like that's two 40 millivolt, that's two 40 millivolt disadvantages and one 20 millivolt disadvantage. This is just 30, 20, 30. So that's not as much of a drop, but it's still not great, right? Like I'd really prefer, like 30 millivolts is starting to get into the range of like, okay, this is kind of noticeable. Especially since then, like, Xtreme LLC is only 20 millivolts lower than Turbo on the set voltage, and still does mostly okay until you get to Linpack, right? For some reason, Linpack really hated Xtreme, where it's now down 40 millivolts. And Ultra Xtreme did surprisingly well for Linpack. But it did terribly in 16K and 112K, where also, like, yeah, so the higher, like, Turbo Extreme, Ultra Extreme on the Aorus Extreme just kind of, why is that actually, yeah, that is 90 millivolts. That's whack. How is it managing that? Because, like, the Asus board just, like, it just gets worse and worse. And then there's Gigabyte where it's like, nope, we don't go below 0.10. Yeah, you don't get more undershoot than 0.10, which is very surprising to me. But yeah, basically, like, once you hit Turbo, you may as well use Extreme. Yeah, on it, like, you're probably better off sticking to something like low, medium, or high. I wouldn't go above high. Yeah, I wouldn't go above high. Turbo's not too bad, but then, like, Extreme and Ultra Extreme have some just wacky situations here and there. So yeah, definitely avoid it. Like, it's kind of the same as the Apex, just the two highest levels avoid. Turbo is debatable. High is definitely fine. Like, high is fine. Medium's fine. Low is fine. But you know what's better than fine? Override mode. So override mode is a new voltage regulation mode that I think originally got introduced on a couple of the Z390 Gigabyte boards, but now they have it on their entire Z490 lineup, and it's ridiculously good at just these tests. So override mode is not static voltage. It's like a weird automatic dynamic voltage mode, I think made by Gigabyte. I'm not sure where it comes. Like, they won't give me a lot of details on how exactly it works. But it is a dynamic voltage mode, and what it does is it absolutely crushes undershoot. But you can see that it's not static because, like, here we're matching, level 4, but then you get to Linpack and you can see the average voltage is up. And the reason it pulls, and my theory, like it pulls up average voltage for LinPack because LinPack is really noisy, so it would normally have a ton of undershoot on any like regular static mode, but on override mode, like override mode just kind of goes like, okay, we're running LinPack now, so we're gonna raise the voltage a little bit to compensate for the fact that LinPack is incredibly noisy. So the actual, A2, the average to minimum spread is still the same, but your absolute minimum voltage is actually slightly higher than if you were trying to do the running matching settings for Prime 95 16K with like static voltage. So that's kind of neat about override mode. And also override mode just does super great in 16K FFT size, and then in 112K it does about the same as static. But again, it does that by raising the voltage up a bit. And there is one downside to it: it raises the overshoot, right? Like because it's pulling the average voltage up, it also lifts up the overshoot a bit. But it's not a huge like it's still not like it's 10 millivolts higher than if you weren't using it. So it's not like, oh whoa, this is a catastrophe. There's so much overshoot. Nah, it just raises it a very slight amount. So it's not a big deal. So yeah, override mode is just great. It also like because the thing that's so cool about override mode is that it gives you a really nice like idle voltage. Right, like this is, and actually this is idle without any power saving is enabled. If you enable the power savings, it'll actually idle at like 0.9 volts. Like it's full-blown dynamic voltage mode, just without you having to actually think about what you're doing. Because you literally, like you punch in 1.36 and you get 1.26. And yeah, depending on the workload, it'll come up a bit. But the thing is, it seems to be more about the noisiness of the workload than the actual like power draw of the workload, which is kind of neat. And with override mode, you should use the auto LLC level. And the reason why you should use the auto LLC level is very simple. You get you get all of the benefits of override mode, but you get the voltage regulation capabilities of the droopiest LLC. Like you can see how the lower your LLC level is, the better the voltage regulation is. Well, override mode gets that really great voltage regulation because auto is even droopier than low. Though, funnily enough, if you're in static and you set it all the way down to, like, the reason I didn't test, like, standard and normal and auto LLC settings is because, well, like, LinPack wouldn't improve, right? Like, we can clearly see LinPack just doesn't care. Even override mode can't do anything about LinPack being, well, LinPack, and it still can't do anything about 112K being 112K. So there's no, like, you won't see an improvement. Like we might see the improvement in 16K FFT size, but we wouldn't see anything in LinPack or 112K. So that's why you have to have a variety of test loads. But yeah, so override mode is pretty cool. I'd highly recommend that you at least try it out, and don't, like, if you adjust the LLC settings, you're literally just going to end up with like they just raise the voltage. Like override mode, from talking to Gigabyte, it's designed to work with auto LLC. You can still change the LLC because the way the LLC is implemented is you're literally just telling the voltage controller to change LLC levels, and this is telling the voltage controller to change voltage levels. So you can technically run override mode with a higher than like change and with like ultra extreme LLC. It's just that then you're gonna have, like, override mode isn't capable of smoothing this over. Right? What override mode does is it gives you a non-stupid dynamic voltage mode, but it still has all of the V droop. So you don't get the voltage regulation issues. So if you actually watch your like vid readings while running override mode, it does very strange things there. But yeah, like in my testing, override mode has just been absolutely freaking amazing. It does so well, right? Like you get, like, because the thing is you can set even lower set voltage than high. And this is especially an advantage if you're on like a 10900K, because as far as I know, override mode is, I think, set to match against like socket sense. So yeah, if you have like a 10900K and you punch in 1.36 volts, you're probably going to get similar voltage. Like it's not like you're I'll need to check this. I think I did check this, and I've just forgotten how it worked out. But yeah, if you punch in 1.36, you're going to get, I think, the exact same dye-sense voltage that I get with the 10700K. So that's the cool thing. Because, like, the biggest problem with the high current draw CPUs is, like, you get steadily more and more droop as your core count goes up. And your current draw goes up. So something like high LLC on a 10900K will actually hit slightly lower voltages. Like if you punch in like high plus 1.375 volts on a 10900K is going to be hitting slightly lower die sense voltage than what I'm getting here with the 10700K. It's going to be slightly lower because it's 25% more cores. You're going to be pulling roughly 25% more current. So it's not going to be a huge difference, but there will be a difference. Override mode doesn't have that issue because override mode is magic. Uh, uh, so yeah, override mode's really cool. There might be also you do need to use like an up-to-date BIOS. There are certain BIOS versions where override mode is horribly broken and don't like it. You'll know it's broken because you'll get hit with 1.55 volts when you try to use it, and just like yeah, don't use it in that case. But if you're like so, make sure you're on a BIOS that override mode actually works, and then override mode is amazing. Um, but you might also want to check like there's a chance that in certain workloads override mode might have a disadvantage against static voltage with like a manual LLC adjustment. I've just not run into that yet. I've just, especially if you disable the power savings, I can't think of a single reason why override mode would be worse than static. You know, because yeah, like if you have the power savings enabled, you might maybe run into a weird scenario where like the voltage doesn't come up quickly enough. So like you're idling at 0.9 volts and the workload starts and you're still at 0.9 volts, then you're screwed. But yeah, so if you disable the power savings, like that should never be an issue because you'll always be at least at 1.33. Um, and it'll pull you up as the current draw increases. So anyway, moving on to the Z490 Unifi. The Unify, if you're on VCC Sense, you should use mode 7, 6, or 5, because by the time you hit mode 4, yeah, it goes 50 millivolts worse, 30 millivolts worse here, and 30 millivolts worse there. So the Unify is kind of interesting because it has very little socket capacitance compared to a lot of the other boards here. But unlike, so the Aorus Extreme actually has an iGPU power plane. This only has vCore. Same for the Apex. Both the Apex and the Unify only have a vCore power plane, and I think that might actually give the boards a slight voltage regulation advantage just because your power plane should have less inductance in it, which can help with voltage regulation. So, and it also has a sort of like, so the thing is the Unify has the front of the socket is full of capacitors. The back of the socket is basically empty, but there's some extra multi-layer ceramics right to the, like on the top layer of the board, which is kind of interesting. So yeah, so I was really expecting the Unify to do horribly, but honestly, if you're at a reasonable LLC setting, it does just fine. You know, it's not really significantly worse than the Apex or the Aorus Extreme in any of these tests. That is until you get to like mode 4, 3, or 2, where it starts giving the Apex a run for its money when it comes to who can undershoot the most with the highest LLC levels. Now, I didn't test mode 1, but I'm pretty sure if we tested mode 1, this would have matched the Apex on the undershoot results. So yeah, because you can see like mode 3, like mode 2 is already hitting 0.11, right? So it wasn't far from hitting the 0.13 that the Apex was doing. Surprisingly, the Unify also, like the Apex, like the Extreme, does quite well in 112K compared to the Apex, even with like the stupid LLCs. But then it really slips up in LinPack, right? Like I think that's actually that's just straight up the worst LinPack result out of all of the testing I've done. And I think this might just be like an intercell controllers versus international rectifier controllers thing. So yeah, because like that's the thing that's like the same on both the Extreme and the Unify. Like they're both intercell VRMs. Anyway, so yeah, if you're on VCC Sense, 7, 6, 5 are fine and basically comparable to, you know, low, medium, high on, even in terms of voltage levels, right? Like very similar voltage settings. Though this board seems to be like, yeah, the voltage matching for me here isn't ideal, right? They're not quite as aligned as I'd like them to be, but the voltage regulation isn't completely out of whack. So yeah, there's still going to be like, there might also be, like, I'm not sure where it would come from, but it might just be a slight difference in how the VRMs are set up on both of these boards. And then again, also my oscilloscope isn't that accurate, so the difference might be smaller than what I'm putting, what I have in the chart here. Anyway, yeah, so 6, 7, and 5 on VCC Sense is fine. When you're on Socket Sense, 5, 4, and 3 are also fine. So yeah, and what's kind of neat about the option to go Socket Sense versus VCC Sense is it kind of gives you an extra, like, LLC step with, like, mode 3. Like, mode 3 Socket Sense versus mode 5 Socket Sense, right? Like, this is what, 1.27? Oh, so this is actually a little high. This should have been at 1.37. Okay, well, no, it literally just shifts all the levels plus 2, minus 2. Yeah, it's like minus 2 across the board. Yeah, if you're on Socket Sense, comparable to like VCC Sense, on a but on a lower LLC level, because again, it just shuffles, like, the board, for whatever reason, the board just shuffles around your LLC slopes, which is kind of weird. But yeah, the board performs fine. The only thing that like, it has more overshoot, which makes sense because it has the least. I think the board technically has the least capacitance out of any board here, and overshoot is where that would be the most obvious. But like, the overshoot is still, like, it's still fine, right? Like, it's only like 10, 20 millivolts higher than any of the other boards in this comparison. So actually, well, yeah, it's 10, 20 millivolts higher than any of the other boards in this comparison. So it's just like, doesn't matter. Right, like, it's not hitting 1.5 volts, so or 1 point, like, yeah, it's just not high enough to be relevant. It's as basically the same as all the other boards. So yeah, the voltage regulation is definitely a little bit weaker, just not in any, like, appreciable amount. So that's neat. Good job MSI on the Unify with that. Then we get to the ITX Aorus board, and that just performs like the Xtreme. Like, literally the same as the Xtreme. Or, okay, wait, so we have 0.3, 0.5, 0.4, so we have 03, 05, 04. We have 04, 05, 05. So that's basically the same, right? This is actually doing slightly better at high, but that's in one test. If we look at LinPack, 06, 07, 07, 07, 07, 07, so that's the same. And then we have 06, 05, 07 versus 05, 07, 06. It's like, the same. So that's really neat. The little ITX board is getting, like, the same voltage regulation performance as the gigantic EATX Aorus Extreme. And this is one of the big reasons why I didn't bother to test the Master, because it's just like all of the all of Gigabyte's boards perform basically is the same. Even the Vision G does, as we're soon going to get to. And then, of course, override mode is just amazing, as is the norm, because it's freaking override mode. So, and it gets the same results as the Xtreme. 0.03, 03, 07, 07, 05, 04. Oh, it looks like it does slightly better over here. And the VRM differences are pretty significant between these two boards. Well, so this uses a bunch of doublers to get up to a 16 power stage V-core. This doesn't have any doublers. It's just a straight 8-phase. They both use 90 amp smart power stages. This has only pause caps for its output filtering. This has a bunch of, like, through-hole polymers, and then also a bunch of pause caps before the socket, and then some inside the socket. And yeah, like, they perform the same. So I was kind of hoping that the ITX would maybe do a bit better. Because, like, sometimes that happens where ITX boards, like, perform like, because of, only having SMD capacitors, and then also because the power plane usually ends up being shorter. ITX boards can sometimes overperform in voltage regulation, even if their VRM ends up running hot, like, because they're ITX and there's no space for large enough heat sinks. But there's kind of not a, like, the VRM on this definitely runs warmer, but the voltage regulation on ITX boards can sometimes be, like, surprisingly good, just because of how they're built. And yeah, well, we're not seeing that here. Like, this really doesn't have any advantage over the Xtreme. It's doing basically the same thing. And then we get to the Vision G, and the Vision G, if you're using reasonable LLC settings, does the same thing as the other Gigabyte boards, which is great news. Like, basically, you could buy any Z490 Gigabyte board that's like an Aorus Elite or higher, and you're gonna get the same you're gonna get the same level of voltage regulation as the Xtreme. So yeah, that's kind of crazy. That's it's kind of, yeah, like, that's kind of crazy. What's most interesting to me is this board doesn't even have any pause caps on it. Like, there's no pause caps whatsoever. And like maybe my oscilloscope just isn't sensitive enough to pick up on whatever difference the pause caps are making, but yeah, I'm not measuring a difference. Um, so yeah. Um, but the Gigabyte boards did like so Gigabyte's boards are doing great. Now I wish I had more boards to compare against, but unfortunately I don't. And then, of course, override mode. Now, interestingly enough, the Vision G's override mode seems to require a lower set voltage to hit the same die sense, which is kind of interesting. So there might be some like override mode difference. Like it might. I think the thing is, I think Gigabyte might be changing, like tuning override mode with various BIOS updates, and then some boards might just have a slightly different implementation of override mode compared to other boards. Because I think, well, this is a 30 millivolt difference in average voltage, and that's still 30, so it doesn't seem to be any more aggressive. And, 0.3, I mean, 03, 07, 05 versus 03, 07, 05, which is the same as the 03, 07, 03, 07, 04 that we saw in the ITX. So, yeah, so all of the Z490 boards I've tested, like, they're all great. Like, they all basically perform the same, which is like I'm kind of annoyed. Like I was really hoping to get some kind of differences, but maybe I just need to get more sensitive test equipment. At the same time, right? There is an argument to be made that if the differences are so small that like they don't show up in like on a 10 millivolt resolution, they're also probably kind of irrelevant. Um so yeah, that's a thing. Um And that's kind of that. So the Gigabyte boards all did a great job. I just kind of wish I had more boards in this chart because obviously, like, the cool thing is every single board I've tested does a great job. Then it's like still, um, I'm wondering, like, is there actually some bad Z490 boards? I guess if I bought one of those super low-end ASRock boards, we'd get a board... Like, we'd finally see a board where the max voltage reading actually is relevant, because that was the only the only Z370 motherboard where the maximum overshoot was actually a problem was a low-end ASRock board. So I'm kind of wondering, yeah, if we picked up a low-end Z490 ASRock, I wonder if we'd get that again. On the other hand, I don't really want to subject my 10700K to a low-end ASRock motherboard. So that's kind of the thing. And also at this point, Z490 is kind of irrelevant. The main reason I'm doing this testing is because once the Z590 motherboards start coming in, I want to see if any of those manage to improve upon the Z490 results, because Z590 is obviously compatible with the 10700K, so I can take my current, the modified 10700K I use for this testing, and I can stick it into all of the Z590 boards, and then we can have more motherboards in this chart. So yeah, that should... Unfortunately, that's not going to change the fact that this chart is mostly going to be Gigabyte boards. I'll try Ask MSI for some extra, like some more Z590 boards. I really want to get a Z590 Godlike into the I really want to test the Z590 Godlike in this, and then I'll probably be testing a Z590 Unify, and we'll see maybe a Z590 Carbon, maybe, because that board comes with a postcode, and that's a good enough reason for me to test one. So, yeah. And this video is still an hour long. Oh, well. I mean, if anybody expected it to be less than an hour, then they're on the wrong channel. So, yeah. Also, I want to do with this kind of testing, I'm thinking I want to do some comparisons against the Z390 boards where I'll downcore because for Z390 and Z370 I was using a 6-core CPU. So I'm thinking I'm going to do some testing with a downcored 10700K, and then I want to retest some of my Z390 boards, because the thing is, with this chart I actually optimized my test methodology to take a lot less time, so I managed to test all of these boards in like 2 or 3 days instead of, like, the last time I was doing this testing, it would take me like a day to do one board. But yeah, now I can do, I could, yeah. Well, actually, I think I did it in 2 days for all of these boards. So yeah, I could step up the number of measurements, definitely, to try. But the thing is, I still don't, still wouldn't address the issue the oscilloscope only goes to 10 millivolts. Like, yeah, it would take out some of the uncertainty, but it would just, like, we'd still be looking, like, it would just be, like, what I basically expect to happen is, like, it would be like, okay, we did a 1.44 volt test, and we did a, like, maybe 1.5 volt test, and at 1.5 volts, we get a difference of zero point zero 0.07, at 1.44 volts, we get 0.07, and then with level 5 at 1.4, and then level 5 at 1.45, we get 0.07 and 0.07, and then, and it would just go on and on, like, so I don't think that would make too much, like, I wouldn't expect it to make too much of a difference, because a lot of these results are just kind of on top of each other anyway. And they're, like, on top of each other across multiple different workloads, which, is not the same as running multiple different voltages, but it's kind of similar. So it's like, yeah, they're probably not going to be that different. But yeah, I'd like to do some Z390 versus Z490 comparisons, because I'm kind of wondering, like, has there been some major, are the Z490 boards significantly better than their Z390 predecessors? I don't necessarily think there's going to be a huge difference. And I'm also starting to suspect that maybe my oscilloscope isn't sensitive enough, because, like, the Apex really, like, the Apex has a socket that's absolutely loaded with multi-layer ceramic capacitors, and there's like 440 microfarads of tantalum capacitors in there as well, and it just doesn't seem to register at all in at least at LLC setting, at least at LLC levels that are reasonable. But then there's also potentially the, like, there's a chance that the reason why I'm not measuring any difference is because we're just hitting the limits of what the CPU socket is able to do. We need more power pins, basically, because, yeah, because basically that's the thing, is, like, you don't, like, if you put all the capacitors on the other side of the socket, like, they still, like, a lot of the switching noise from the CPU isn't necessarily going to get all the way out of the CPU and to the CPU socket. Which might explain why MSI is doing so well with a CPU socket that looks so empty. Actually, it doesn't even, like, it is empty. Like, there's barely any capacitors on the back. So, yeah. Anyway, that's it for the video. So hopefully you found this somewhat interesting. Yeah, thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store, where you can pick up shirts, stickers, posters, the usual YouTuber merch. Both of those help out immensely with running the channel. They allow me to do things like, buy 10700Ks so I can attach coax to them, and of course acquire oscilloscopes and that kind of thing, as well as the Apex, because I did have to buy this board. I was really hoping it would, like, properly top the chart, though, and it just didn't. So now it's like, yeah, we need to get an oscilloscope that makes the Apex look better. Though there's still a very real chance that there just isn't a difference at this point. Like, the boards are just so good that the limit isn't the motherboard anymore, it's just the CPU socket. I should try solder. Well, no, I need to, like, there's a stuff I'm doing on Z390 that's trying to test for that. Fortunately, it's been very difficult to implement. But yeah, anyway, so if you'd like to support the channel, Patreon, Teespring, links in the description. And that's it for the video, so thanks for watching, and goodbye.